This is going to be the first lecture from Chapter 7, and we're moving on now to the study of the atom. In particular, we want to understand where the electrons are located in an atom. So we learned before that the electrons are located outside the nucleus of the atom, but we want to understand in more detail what exactly those electrons are doing. And it turns out that because atoms and electrons are so small, a whole new field of physics had to be developed to explain the properties of atoms, and that became known as quantum theory. So we're going to be going over some quantum theory. Now, to understand quantum theory, we have to understand how light and other types of electromagnetic radiation interacts with atoms. And since light is a type of wave, we're going to start out with a really brief overview of some properties of waves. And so this lecture is covering section 2 of chapter 7. So this picture here from the textbook shows a simple wave, looks like just a sine wave. So the first property that we can talk about is called the wavelength. And so the wavelength is just defined as the length from a point on the wave to the same point on the next cycle of the wave. And as you can see, it's usually defined as the distance from the peak of one cycle of the wave to the next peak. As with any quantity, wavelength needs to have a unit, but since wavelength is just a length, the usual unit of length, which is the meter. Now, by the way, the symbol for wavelength, this is the Greek letter lambda. So lambda then is the symbol for wavelength. The next quantity we can talk about is the speed of the wave. So you may be aware that different waves travel at different speeds. Light waves, for example, travel faster than sound waves. So the speed, which we symbolize as u, is just how fast the wave is traveling. But really, for this class, we're only concerned with electromagnetic radiation, and that makes life a lot easier because all electromagnetic radiation travels at the same speed. And that is about 3 times 10 to the 8 meters per second, and we symbolize that with the letter c. So for what we're going to do, we can just consider speed to be a constant c. And that c is also referred to as the speed of light, since light is a form of electromagnetic radiation, and all electromagnetic radiation travels at that speed. And of course, the units, as you can see there, of speed would be meters per second. The next property of the wave is called the frequency, and that's symbolized by the Greek letter nu. Kind of looks like a V, but it's actually nu. And so the frequency is the number of cycles of the wave that pass per second. So for example, if you're looking at waves in the ocean, if you were to count how many waves pass by each second, that is the frequency. So the units of frequency are just, since it's the number of cycles per second, we use the unit of inverse seconds, We usually write that as seconds to the -1 power. And that's also known as hertz, which is given the symbol Hz. So Hz is pronounced hertz, but hertz are really just the same as inverse seconds. So if you're ever given a frequency in hertz and you need to do a calculation, just consider it to be in 1/seconds. So we've talked about wavelength, speed, and frequency. Now there is a relationship between these three quantities. They're not completely independent because the frequency, the number of cycles of the wave per second, is going to depend on, first of all, how fast that wave is traveling, and it's also going to depend on the wavelength, because the longer the wavelength, the longer it's going to take each cycle to pass by. So in fact, we can say that the speed of the wave, for any wave, the speed is equal to its wavelength times its frequency. Now what this means is, now since we've said that for electromagnetic radiation, the speed is always the speed of light, that's a constant, that means that if you know the wavelength, you can solve for the frequency and vice versa. So for example, the wavelength of electromagnetic radiation, lambda, is always going to be the speed of light divided by the frequency, and then we can also say that the frequency is equal to the speed of light divided by the wavelength. So if you have frequency and want wavelength or vice versa, all you have to do is take the speed of light, divide by the wavelength or frequency, and then that gives you the other quantity. One more property of the wave dimension is known as the amplitude. And as you can see on the picture here, that's just the height of the peaks. And that corresponds to the intensity of the wave. So for example, for sound waves, a greater amplitude would just mean a louder sound. So for light, it has to do with the intensity of light. In other words, how bright the light is. Okay, so this picture, figure 7.2 from the textbook, then illustrates some of these ideas. On the left there, you can see three waves with the same amplitude, but notice they have different wavelengths. The one marked A is longer, B is shorter, and C is even shorter. And if this was visible light, then those different wavelengths would correspond to different colors of light. And then the waves on the right have the same frequency, but they have different amplitudes. You can see the one on the bottom has a greater amplitude, so it would be more intense than the one on the top. Now, I have mentioned that we're interested in electromagnetic radiation, and all electromagnetic radiation travels at the same speed, 3 times 10 to the 8 meters per second. But the radiation can have different wavelengths and frequencies, and depending on the wavelength or frequency, it determines what type of electromagnetic radiation the light is. And that is shown by the electromagnetic spectrum, which shows you the different types of electromagnetic radiation. So on the left side here, you have, so this would be low frequency. And by the way, this is a mistake from the textbook. That should be nu, the frequency. And also that corresponds to a longer wavelength. And so as we're going to see in a minute, this also corresponds to low energy. Then as you go to the right, the frequency is increasing. So on the right side, you have high frequency, which is also high energy, and that corresponds to a shorter wavelength. Now notice on the left side, the low frequency end of the spectrum, you have radio waves. So radio waves used in communications. And a little bit higher frequency are microwaves. Of course, microwaves are used in microwave ovens in your kitchen. Also, you may not be aware of this, but Wi-Fi signals are microwaves. So if you're watching this video connected to Wi-Fi, then the data is getting into your computer through microwaves. Now, at the other end of the spectrum, so very high frequency and short wavelength, which is high energy, then we have X-rays as well as something called gamma rays. In between, we have visible light. Now, a little bit higher frequency than visible light, we have UV, ultraviolet. A little bit lower, we have infrared, or IR. But in between, then, is visible light. So visible light is light that we can see. So electromagnetic radiation in that range can be seen by human eyes. And as we said already, depending on exactly where you are in the visible region, then gives you the different colors, going from at the lowest frequency or the longest wavelength is red, passing through all the colors of the rainbow to violet. So you should know the wavelengths that correspond to visible light. You don't need to know any other wavelengths of any other types of radiation, but you should know that visible light is this region, 400 to 750 nanometers. So if the electromagnetic radiation has a wavelength within that range, it's visible light. So again, this prefix N here is nano, and that corresponds to a billionth. So 1 nanometer is 10 to the minus 9 meters. So we can also say that visible light, then 400 is 4 to about 7.5 times 10 to the minus 7 meters. So that was an introduction to waves and electromagnetic radiation. Now we can move on and get into quantum theory. So quantum theory was developed around the beginning of the 20th century, and it came about because there were some phenomena that scientists had observed, but they could not explain by what was known at the time. Now we refer to that as the laws of classical physics. So classical physics could not explain certain things. One is called black body radiation, and you may not know that term, but you certainly experience it. It's the idea that when objects get really hot, they emit light. So when things are red hot or white hot, so for example, as in the picture here, the glowing coals, hot coals that are glowing red, you've probably seen electrical elements. When they're hot, they sort of tend to be an orange color. So scientists didn't understand why should these objects glow these colors when they get very hot. Then there's something called the photoelectric effect, which we're going to be talking about in a minute. And then something called atomic spectra, which is the idea that each element gives off certain wavelengths of light. And that will be the topic of the next pre-lecture video. But going back to blackbody radiation. So this was studied by a German scientist called Max Planck. And as he was studying blackbody radiation, he came up with a hypothesis that substances can only emit certain amounts of energy, which were referred to as quanta of energy. And then he did some calculations, and he noticed that the amount of energy given off by these hot objects then was proportional to the frequency of light. And this was a new idea because prior to this, there wasn't thought that there was any connection between the energy of light and its frequency or wavelength. Maybe only the amplitude affected the energy of light. But Planck said no, that the energy of light depended on the frequency, and so he said that energy of light is proportional to the frequency nu. And so he came up with this equation that E equals h nu, where h is a constant that's known as Planck's constant. And you can see the value for it there. It's a very small number, 6.626 times 10 to the negative 34 joules times seconds. So then when you multiply Planck's constant by a frequency in 1 over seconds, then that gives you an energy in joules. And Planck's work helped to understand something else called the photoelectric effect. So the idea there is, as you can see on the picture on the left, you have a metal plate and you shine light on that plate, and under certain conditions that light can cause electrons to be ejected from the metal. On the right you can see the full setup, and so light causes electrons to be ejected from the metal. Those electrons are trapped by this electrode, and then that completes the circuit. So if you see current flowing on the meter, it shows that the photoelectric effect is working. Now it made sense that light could have enough energy to remove an electron from a metal surface, but what was confusing about the photoelectric effect is that it was found that in order for it to occur, that light had to have a certain minimum frequency. That was known as the threshold frequency. So if the frequency was above a certain amount, the photoelectric effect would occur, and if it was below that amount, it would not occur. And this was not what was expected. People would have thought, well, maybe the amplitude of the light, if the light was intense enough, it could cause the photoelectric effect to occur. But it turns out amplitude was not a factor. It was only the frequency that mattered. And also it was found, even if the frequency of the light was too low, even if you waited a long time maybe for energy to build up, still you never would see an electron coming off. If the frequency was large enough, the electron would come off immediately. Otherwise, if the frequency was too small, it would never come off at all. And the photoelectric effect was studied by Einstein, and he published his work on this in 1905, and he got the Nobel Prize in 1921. And of course, Einstein is known for many different discoveries, but this was the only work that he got a Nobel Prize for. And so Einstein noticed Planck's work and his idea that the energy of light depended on the frequency, and so that then made sense. That then explained why light would need a certain frequency for the photoelectric effect to occur, because that affected the energy of the light. But Einstein went a step further, and he said that light actually comes in little packets that he called photons. And the reason why this was important is because up to this point, it was thought that light was just waves. But Einstein was saying that you have to think of light as also having the nature of particles, the idea that it has a certain size. And so this is a very important idea from quantum theory, the idea that electromagnetic radiation then has the property not just of waves, but as particles also. And so that explained the photoelectric effect. It was the idea that photons of light then hit the metal. If the photons had enough energy, the photoelectric effect would occur and electrons would come off the metal. If their energy was too low, then it would not occur. And so the energy of the photon is given by, well, really you get it from the same equation that Planck came up with. So we can say that the energy of a photon then is just Planck's constant times its frequency. Now we saw earlier that the frequency of electromagnetic radiation is the speed of light divided by its wavelength. So if we replace nu there with c divided by lambda, we can say that the energy of a photon then is h times c, two constants, divided by the wavelength. So here are two relationships then between the energy of a photon and its wavelength or frequency.